Hello everybody, today we're going to be going over the find the largest island problem. In this problem we're given a two-dimensional grid of zeros and ones, as we can see here. Our goal is to find the size of the largest island. If there is no island, we're just going to be returning 0. And how we would define an island is a group of ones connected vertically or horizontally. So like these four. So as we can see in this example right here, we have a grid which is basically a matrix, 3 lists inside of a list in a 2D format. In this list we have 4 ones up in this top corner here. You can see how they're connected all horizontally and diagonally. These zeros are just like whatever, nothing. You could consider them the water if this is an island. And this one down here, since it's not connected directly horizontally or vertically, it's only connected diagonally, which doesn't count. It's its own separate island. So essentially, since these 4 are connected, this is the largest island, and the size of that island is 4. So the final output in this specific grid, if this specific grid was an input, would be 4. Alright, so now to start off, we gotta let's create the function def max underscore island size, and we know that it's going to be taking a grid as the input. Now to solve this problem, we can use a graph-based approach. Essentially, since we're dealing with lists inside of a list, it's a matrix, which we can also define as a graph, because a graph is basically a series of interconnected nodes, and we can treat this grid, the grid that we input, as a graph because it has multiple different nodes that it can traverse to. In particular, when we find an island, we want to traverse up, left, right, and down to check to see the connecting nodes in between. So the way we could do that, we could use either a breadth first search or a depth first search traversal method, which are the most common method, basically the 2 different methods of traversing a graph. But in this case, the simpler version is to do a depth first search using recursion, so we're going to be doing that. So the first conditional statement that we're going to get is that if the grid doesn't exist at all, obviously. So if not grid means that if the grid doesn't exist at all, or if the first row doesn't exist, if grid of 0. If grid of 0 doesn't exist, then we could just return 0, because we essentially know that, okay, if the grid doesn't exist or the first row of the grid doesn't exist, we know that, okay, the grid is basically empty. So we can just return 0 because there would obviously be no island in an empty grid. Next, let's define the way we're going to be traversing the grid. We'll do this by setting up 2 variables, rows and columns. The rows is just going to be the length of the grid. So for example, this grid, the length would be 1, 2, 3, because that's the number of rows that are there. And columns, we could just separate it with a comma, length of grid of 0. So that's going to be the length of the first row, that's the number of columns. So since the length of this list is 3, there are 3 columns, as you can see here. 1, 2, 3. Alright. Next, we're going to create a visited list. Basically, we're going to be setting up basically a matrix that'll indicate essentially the same thing. We want to create the same thing here, except instead of ones and zeros, it's just going to be false or true to depend on whether or not it's visited. So to create the thing, we can create a list inside this list. False for, let's say, x in range of columns, So what this will do is it'll loop through each of the columns in this grid and then just make 3 falses, for example, and then we multiplied that 3 times. So we say 4x in range of rows. The variable doesn't really matter here. It could be different or the same, but essentially what this creates is this visited array creates a 3x3 list of Boolean variables, true or false, whether the index we're at has been visited in the past. Next, we're going to actually make our depth first search traversal method to go through the tree. So we'll say RNC. I could do rows and columns, but RNC is the best way to just make it quicker. Now let's define the base conditions. So when would our depth first search stop? Our depth first search would stop if we exit the grid. So for example, if the row is negative, it's a negative value, then obviously that couldn't be possible because the row value would have to start at 0. So we can say if r is less than 0, or if the r is greater than the maximum length of this. So if it's greater than 3. So we can just say, or r is greater than or equal to 3. We would do greater than or equal to 3 because the index here would just be 2 actually. So if it gets to 3, we know that okay, it's the row is outside of the thing. So we'll say or r is greater than or equal to 3. Sorry, we already have this. We're not 3. It's gonna be rows, which is the length of the grid. And then we'll do the similar thing for the columns. C is less than 0, or C is greater than or equal to the columns variable that we defined up there here. Alright, next. Oh, yeah, shoot. Sorry, I forgot. So if we exit out, so once we exited out of the rows or the columns, we'll just return 0. And also, we just return 0 if we see that the place we're at is 0. So if grid of R and C is equal to 0, or if it's in the visited list we just created. So if the visited is true, then we would just say, we would also return 0, because we already know that we visited the thing, there's no reason to go back to it. So we would return 0. So these are the 2 base conditions for determining when the DFS would close. Now, other than that, other than immediately breaking out of the base condition, we would know that the place we started off is true, because we're just going to start by setting the place we are at in the visited array as true, so that we know, yes, we visited this section. We're going to have a size variable to like track the size of the island, because if we see it's a 1, okay, we start to count, like, okay, we're starting to count that this is an island. So we see a 1 here, so we'll start to count, and we count in each direction. So this is where we start calling our function recursively. So first we'll search in the up direction, and to search in the up direction, what we would do is just say r minus 1 and then C. So basically we're calling the same function, except, sorry about that, we're going to be calling the same function, except we see that the r value is going to be less than 1. So if it's going to be, if we're at 1 for example, to search upwards we would want to go to r of 0, but the column stays the same. So we would call the function recursively r1 minus r minus 1 of C, and then to search down we would just do the opposite. I could actually just copy and paste this. And as you could imagine, we'd essentially do the same thing for the left and right. To search left in the columns, we'd go -1 and +1 to search to the right. So now essentially that's going through the breadth first search traversal. I mean, not the breadth first search, the depth first search traversal of the island. So once we go through this entire thing, we would determine that, okay, now that's an island. At the end of this, we would just return the size. Alright, so we got that depth first search down there. Now all we need to do is continuously run this over each one, because for example, if we just get to this one island, so we see that this is the 4th island, and it'll just return out the size of 4 there. But we need to know that, oh, this is not the biggest island that's possible. Like, what if there was an island over here that was bigger? Obviously in this problem there isn't, but what if there was a bigger island somewhere? So to do that, we just loop through this entire thing to do the same operation in each individual square. So for R in range of rows, for C in range of columns, this is going through each one. Now we'd say the grid of R and C. So if we say that it's equal to 1 and it's not already visited, so we didn't mark it already in our matrix, then it's worth looking to see, then it's worth performing a depth first search to see whether or not there is an island here that's worth matching. So if these two conditions are true, then we'll perform a depth first search of R and C. But what we want to do is we want to say max size is equal to this. So we're setting this max size variable is equal to this. But then obviously, if for example this was like a huge number, right? Like right now it starts as 0, right? But what if we found an island of size 1, but then we wanted to go to 4 or something like that? No. What if we already calculated this 4, for example, but we have this island of 1. We don't want to just overwrite it, so we would do a max call, and then we'd take the max between this and max underscore size. So this would be comparing this variable to whatever we get in this DFS approach, DFS search of this island. So yeah, this is basically just running through all the possible islands, and now at the end here we just return max size. To test this function out to see if we did everything right, let's just print out the max island size thing that we just created. Max island size of, let's say, grid, and then let's define grid over here. So the grid would look something like this. So now let me clear this out. Had some stuff there from before. Now we can run this code and we would expect the largest island to be 4, and we get the 4 there. So that's pretty cool. The code is working as intended. We can test, for example, connecting this island to see, okay, so we have these 4 here connected with these 2 over here. We can run the code, and yes, we see that the island expanded. So now the biggest island would be this whole entire thing, which would be 6 there. And yeah, we could keep testing, see if this one should return 3, because that would be the biggest island, and it does return 3. So yeah, that's basically how this problem works. Essentially, we just used a graph and then a depth first search approach to complete the problem. Okay, hopefully you guys enjoyed that, and if you liked it, be sure to like and subscribe. Alright, see ya.